I'm Laura Allen, for those of you who don't already know me. I'm a PhD student in Danielle and McNamara's lab at Arizona State University. And today I'm going to talk to you about some of the research I've been doing looking at the temporal dynamics of the language in students that students are inputting into a reading strategy tutoring system. So like I said, today the focus of my talk is on discourse. So just as a really quick, before I really get started, I just sort of wanted to highlight how encouraged I've been by this conference this year and how much there has been such an emphasis on discourse. So I went to my first LAK 2 years ago, and I felt like the weird person with, not many people were studying language, and I feel like now we're in discourse 3 of the whole week, and that's pretty cool. So why should we study discourse? I probably don't need to go into this for all of you now, but discourse is really important, and it's really important when we think about the way that students are engaging in classrooms, the way that students are learning. So it's a means of interacting with our community, our world, and it's a means of learning through information. So we use discourse when we make friends, when we socialize, when we begin to learn language, when we're developing as students. But we also use discourse in a lot of other means when we're reading our news in the morning, when we're choosing what news is real, what news might not be so real, when we are listening to our politicians telling us what's going on in the world, even when we're engaging on Twitter, and that's the LAK hashtag, so I'm not really into Twitter, but all of you seem to be very good at doing discourse through Twitter. So, but there's one problem, right? And it's hard to understand the language of others. It's sometimes hard. We have to assume the knowledge of other people when we're communicating with them, and then we also have to make a lot of inferences when we're trying to understand what other people are trying to tell us. And this is particularly true when the language that we're processing is conveyed through text as opposed to spoken communication, right? So when you're having a conversation with someone and you don't understand what they're saying, or you don't have enough prior knowledge of to make the inferences that they want you to make, you can just ask them a question, they can respond, they might even read your feedback and do it automatically. But when we're reading text, the texts are static, and so we have to engage in different types of processes that require us to make connections across the text in order to use our prior knowledge to understand. And so there's a lot more challenges associated with comprehension of text that might not be as true for normal other types of discourse. So we need to rely on our domain knowledge as well as our strategies, our vocabulary knowledge, and we need to be engaged with the task enough to even process the information. And so, not surprisingly, given this difficulty, students tend to underachieve on national test of reading proficiency. This is within the United States, only about 25% of students leave high school proficient in reading comprehension, and there's similar problems that persist throughout other countries besides the United States as well. So in response to this need, a lot of researchers, especially within our community, have developed educational technologies that provide adaptive instruction for students in terms of literacy. So they provide students with scaffolds and adaptive feedback that will allow them to learn how to read and learn how to communicate with others through text. And so these have adaptive content, many of them, so they can adapt the difficulty of the text that students are reading, for example, the content of the text. They can personalize the feedback, so this is both summative types of feedback, giving you a score about how well you're communicating with other people, whether or not you're being clear, but also formative feedback. So if you're struggling in certain areas, what are strategies or what are some things that you can do to adapt the way that you're comprehending or producing? So how can you change that? And then also individualized instruction as well. And so one example that I'm going to talk about a little bit today, but not go into very much, is iStart. And so iStart is a tutoring system that we've developed in our lab that provides strategy training on self-explanations. And briefly, self-explanation is a strategy that you can use to, when you're engaging in some sort of task, like reading comprehension, or reading a really difficult text that you don't know a lot about, you can explain it to yourself, and you can use your prior knowledge to explain that to yourself. And that's been shown to help students comprehend things at a deeper level. And so in iStart, what we do is we provide adaptive instruction for students on strategies that they can do to self-explain. And so some of these are things like paraphrasing the material, so putting it in your own words, but then also, and perhaps most importantly, strategies that prompt students to make connections across the text. So we know that requiring students to not just engage in the individual sentence that you're reading or focus so much on individual words, but really to start making connections across the text and to their own prior knowledge is really important for being able to understand what you're reading. And so that tutoring system focuses on that. But broadly, in terms of these types of adaptive literacy technologies, they focus on really trying to change the way that they're adapting content to students' needs. And so they adapt content based on students' performance, so who's doing better and what types of scores are they getting in the system. But also they focus on specific skills, so they try to focus on if you're doing well in one particular skill, but maybe you're not doing as well in other skills, adapting those things as well. But also engagement, so when are students getting bored? When are they starting to mind wander, like Sydney was talking about this morning? And so what can we do about that to adapt instruction? But there's one problem when we're thinking about literacy instruction with these adaptive educational technologies, and that's that performance in ill-defined domains can be extremely difficult to assess. So when we think about performance in a math domain, there's generally a right and wrong answer. So if the answer is 4 and you put 3, you're wrong. I mean, there's only so many ways that you can think about that and talk about that. But with reading and writing, it's a lot more difficult. So if you don't understand what someone's trying to convey to you when you're reading a science text, where did that comprehension break down? Do you have some understanding and then you're just missing a little key piece? Are you really just missing the whole point? Can you decode the words, but are you not making connections, or is it that you don't know the words and what they mean? So there's a lot of different reasons, and that can make it very difficult to assess, especially in an automated way. And so one thing that people have looked to in terms of increasing adaptivity in these literacy-based adaptive technologies is natural language processing. And so natural language processing provides us a means through which we can automatically analyze natural language that's been input into a text and then provide adaptive responses and adaptive instruction. And so one thing in these systems is that natural language processing has been starting to be used to drive scoring engines. So many of you are familiar with automated essay scoring. That's become really big and controversial in a lot of testing services. And what these systems do is that they're taking features of the language that students are producing and then using machine learning to build algorithms that will drive holistic scoring. So when you write an essay, you might get a score between 1 and 6 on your essay, and it'll tell you, okay, this is about a 3, it's about a mediocre essay. But one thing that's often underutilized about natural language processing, and what might be more useful when we're thinking about actually remediating instruction and providing formative feedback, is the more fine-grained aspects of language use. And so rather than just thinking about, oh, this is a 6 or this is a 3 on an essay because it's got big words and it's got paragraphs at all, then one thing we can think about is what are the different features in the essay doing, and where did you succeed and where did you not succeed? And so moving into that area, a number of different linguistic features have been found to be predictive of performance on both text comprehension and production tasks. So for example, we know that essays that are more lexically sophisticated are also tend to be rated as more high quality, but they're also associated with people who have higher vocabulary knowledge, right? So you can think about the fact that if people are using higher words, you might be able to get some sort of proxy of their vocabulary knowledge from that. Then you could contrast with something like semantics. So what types of content are they talking about? And so some students might have high knowledge of something, and that might be driving their score, but they might have lower lexical sophistication versus the opposite, where one student has big words but not the right content. And those students might need different types of instruction, and those linguistic properties can tell us something about that. So you can also use NLP to look at argument strength, for example, as well as syntax, or using complicated sentences or using the same sentences over and over and over again. So all of those are things that we can ask using NLP. So another thing that we seem to be missing, though, in thinking about these different sorts of things is that we're not really focusing on the processes that are underlying discourse comprehension. So at the end of the day, what we're doing a lot of this time with natural language processing is that we're taking some final product that a student has completed. So an essay they've written, some sort of self-explanation that they've produced while they were reading the text. But then we're always analyzing it after the fact. We're not thinking about what they're doing while they're actually reading the text or writing the text. What are those processes? And can we use automated language analyses to tell us something about those processes? So there's been a decent bit of research on the reading process, not in these automated situations, but by other types of cognitive researchers. And so by integrating that sort of research, but thinking about what sort of connections students are making across the text, like I was talking about earlier, whether or not they're having pauses, or whether or not they're only focusing on individual sentences and making these different types of connections while they're reading. It can help us to understand the cognitive processes of reading, but also help us to provide better types of formative assessment and feedback to students, which can give greater context for the scores that they receive in the system. So moving away from providing students with this holistic scores and really thinking about providing feedback that's helpful for them. So one way that I've been thinking about doing this is thinking about the dynamics of reading. So when we're thinking about reading, we're not just thinking about, right, did you read the essay? Did you understand the individual words? But really, what were the dynamics? Were you focusing on the connections? Were you repeating and making links throughout the text that you're reading? And so I've been moving towards thinking about modeling dynamic reading as a dynamic system. So there's a lot of research that's been gotten more popular lately in cognitive science, thinking about complex dynamic systems and how cognitive processes unfold over time. And the focus of these is that when you're thinking about complex systems like learning, like comprehending from text, then what you really have is, well, where we're having errors is when we're focusing so much on individual level mechanisms, we're missing the bigger picture of these complex systems. But really, if we think about it, we shouldn't be focusing so much only on individual effects and thinking about the fact that these systems are interacting in complex ways. There's interaction dominance in these systems. And what that can do is lead to interesting properties that can be subjected to nonlinear modeling. And so moving away from only thinking about decoding leads to sentence comprehension, leads to understanding of the text, thinking about these things in a more nonlinear type of way. And so in this study and in our bigger picture study, our approach is to develop assessments of students' reading processes that move beyond holistic scores. And then leverage these assessments to develop instruction and feedback that's more sensitive to individual users. So moving away from that focus on holistic scores and thinking about these dynamics and thinking about these fine-grained properties and how they're interacting to better adapt content to students. So in this study, what we're doing is we leveraged a dynamic technique called recurrence quantification analysis to analyze just the temporal patterns of students' word use in text. So just because this is a first study, we're not doing anything complicated at multiple levels of language. We're only focusing on individuals' word use, just to see whether or not there are interesting nonlinear temporal patterns in their language use that provide interesting and helpful information about the way that students are interacting with text. And so recurrence quantification analysis is a nonlinear modeling technique that can provide information about when a complex system returns to different types of states. And so this system can be used, or this methodology can be used for both continuous and categorical data. But here we're going to focus on it for categorical data because we're purely going to look at whether or not students are returning to specific patterns of word usage over time. And so some research recently, those are backwards, have shown that you can subject recurrence quantification analysis to language use. So Rick Dale and Michael Spivey have done some interesting work looking at recurrence of child and caretaker speech and how those provide information about the way that people are talking to students and how that relates to development. And what this does is, it's really interesting, right, is that recurrence quantification analysis provides us a means to understand how students are, behaviors are unfolding over time. And so you can visualize the way they're doing it through recurrence plots, which I'll explain, but then you can also take those plots and quantify and provide and get quantitative information about the recurrent properties of students' word use. And so like I said, today we're only going to focus on categorical recurrence quantification analysis. But if you're interested in knowing more about continuous, I can talk about that later. So, I don't know why that happened again. So how does this all work? How does recurrence quantification analysis work? So the starting point of RQA is the development of a recurrence plot, and this is really the key part of it. And this is a visualization of the matrix, of a matrix, where the individual elements represent points in a time series that are visited more than one time. So anytime they recur, for example. And so this plot is just showing times when a time series repeats any sort of behavior, and you can define that behavior however you want. And so in terms of categorical recurrence, if we're starting with language, then what we'd first need to do is convert transcripts or convert essays or whatever we're looking at to a sequence of numerical identifiers. So this is just kind of a silly example, but just to show you. Say we have the sentence, the ice cream man brought ice cream on Friday. So what we would do is we take each of those individual words and give them a number. And the number doesn't really matter in terms of the, it's just a categorical code. And so the becomes 1, ice becomes 2, cream becomes 3, but then you see in this sequence of numbers, then when you repeat ice again, you go back to 3, and so it's just showing anytime you repeat the behavior. And so here we're focusing on words, but you could do this at the level of this, you could do it at the level of bigrams, you could do it at the level of individual letters, you could do it for any sort of thing beyond. It doesn't have to be words, that's just what we're doing here. And so anyway, so then what you get when you do this is you get a recurrence plot. And this just provides you an overall view of the time series trajectory through its space. So when you think about the fact that complex systems are moving through a space, then you see where it starts recurring and repeating different systems of behavior. So anyway, we're going to go back to the example just to show you what I mean by that. So to generate the recurrence plot for this sentence, the ice cream man brought ice cream on Friday, what you would first do is you place the sentence, or it could be the entire text, whatever you're modeling, both on the x and y axes of just a two-dimensional plot. And then you start putting a dot every single time something recurs. Right, so because this is symmetrical, this is recurrence analysis rate, so it's against itself. So then you're going to automatically have a diagonal line on the middle, and that's called the line of incidence or line of identity, and it's just always going to be the one in the middle, right? But then what's interesting, right, are these other plots that are not on the line of identity, and so those are recurrent points. So anytime the system repeated some sort of behavior, then you have these other plots, and then you get diagonal lines when it repeats something continuously. So ice cream is getting repeated again, and that's 2 words in a row, so that forms a diagonal line, and you can analyze things about those lines as well. So okay, those plots are interesting. They provide some interesting information about systems that are repeating and the behavior of those systems. But right, we obviously want to get numbers out of this. We're all data science people or something of that sort, and so we want to be able to understand what that's telling us. So that's when we can subject these plots to recurrence quantification analysis. And this captures information about the distribution and the amount of points that are recurring throughout any sort of time period. And so you can get information about the rate of recurrence, determinism. I'll go through all of these, but you can get multiple different types of measures that quantify those plots. And so I'll go over a few of them briefly, and then I can talk about them later. These are not in any means all of the things that you can quantify, but these are the sort of very popular ones. So first you can get a measure of recurrence rate. And what this is just the percentage of plot occupied by points at all. So, and this is all of these are taking out the line of incidence because that's not, it doesn't matter. The next is the determinism. So it's the percentage of the points on the plot that fall on diagonal lines. So that provides information about the distribution of recurrent points in the plot. So are you only repeating individual words, or are you repeating entire sequences of words when you are repeating? You can also get the length of the diagonal lines on the average. So are you repeating what types of sequences? Is it bigrams? Is it individual things? Is it long periods of things? Which is really cool if you ever do this on songs, because you can pick up on the chorus and these long lines throughout the point. You can look at maximum line length, so when did someone repeat some one long sequence at some point? You can see if they did that. And then you can get the entropy of these line lengths. So what is the distribution of the line lengths in the recurrence plot? So this is just showing the degree to which the trajectory of the system exhibits order, or whether or not it's stable or not. So anyway, in the current study, what we did is we did recurrence quantification analysis on students' language in an intelligent tutoring system, in that iStart tutoring system I talked about earlier. And the purpose of this was to investigate the degree to which cognitive processes of reading comprehension can be examined through these dynamical analyses of natural language responses to text. And so what we do is that we take the visualization, so we take the recurrence plots, and then we subject it to RQA and get quantifications of these things to see whether or not they relate to students' comprehension on their text. So in this study, we had 149 high school students, and they came into the lab and they completed a self-explanation task while they were reading a science text. And so what this means is that students were reading a complex text, and throughout it they were prompted to provide a self-explanation like I talked about earlier. So explain what this text is talking about. Explain this to yourself. And so what we did is that we took these individual self-explanations and we aggregated them for each student. So we had a file that had all of their self-explanations that students had produced while they were reading to get this sort of information about how they were thinking while they were reading the text. And then we cleaned these and then we converted them into the categorical codes like I talked about earlier. And then beyond that, we also calculated text-based metrics that are calculated at the aggregate level. So we calculate, which I'll talk about in a second. And then at the end, students answered text-based and bridging comprehension questions. So text-based questions are questions that you can answer by looking at an individual sentence in the text. They tell you whether or not they're getting at that surface level understanding. And then comprehension bridging questions are ones that ask you to tap into understanding how to make connections. So students who actually had to, in order to answer these questions, you have to be able to make connections across multiple sentences in a text. And so, like I said, we calculated measures, aggregate measures of the text. So we got the total number of words that they produced in their self-explanations. We got the number of letters per word, so how big were the words, as well as the type token ratio. So what's the ratio between unique words as well as versus total number of words in the text. And so all of these were just to see whether or not, to control for the fact that we can already get aggregate measures and to really see whether or not these dynamic measures of word use provide any additional information about students' text comprehension. So then we also calculated multiple recurrence measures. So I talked about these earlier. We looked at recurrence rate, determinism, the number of lines in their plot, the maximum length of the line, average line length, entropy, and then we also did a normalized entropy score for the number of lines that were in the plot. So, looking at our results. So I'm going to show you, before I go into the quantitative results, just two plots for a student who got a low comprehension score and a student who got a high comprehension score, just so you can see sort of the difference in these two types of plots and to visualize the distribution of the words in students' self-explanations. So this first plot is an example of a recurrence plot for a low comprehension student. So a student who got a low score, they actually get a score of 1 out of 8 on this comprehension test. And just so you know, these both had almost the exact same number of words. One had 224 number of words and then one had 251. So they're very, very similar compared to everyone else. And so what you see is that this student does not making many connections. So they have some recurrence in their plot. They are repeating some words over time. But when they do, they're not really connected. They're not in like long sequences of anything. They're just repeating different words over time. And then if you can compare that to the high comprehension student, what you see is this very different pattern of behavior. So the student who received a high comprehension score, they overall have more recurrence happening in general, so they just have a higher recurrence rate, which you can see pretty qualitatively. But then when they do have recurrent points, much more often, these recurrent points are falling on diagonal lines. They're repeating entire sequences of words as opposed to just random words over and over again. So something like the might not be meaningful if it's repeated over and over again, but the talk or the cell or, cellular division or something like that is going to be more meaningful, so these bigrams. So then, like I said, what we did is we then subjected these to the quantitative analysis, so the recurrence quantification analysis, to empirically test these qualitative observations. So we first calculated Pearson correlations between the RQA indices and students' comprehension scores. And what we found was that students' comprehension scores were significantly related to multiple of the RQA indices. And so in particular, these skilled readers didn't simply seem to be repeating words, which we saw in the plots already, but they differed also in their the length of their lines from the other students. And we also see that there's difference between the bridging comprehension questions and the text-based comprehension questions. So bridging was more strongly related to the recurrence quantification indices in general, and they also showed different patterns of behavior. So we subjected these to regressions as well, just to see how much variance they were accounting for. And this included the text-based measures as well. So the summative measures as well as the other measures. And what we found was that total comprehension, text-based comprehension, and bridging all yielded significant models that included a combination of the aggregate measures, but also included these temporal measures as well, that showed that things like log of line number and number of letters per word, determinism, and entropy all related to students' comprehension on the test. And so what these show is that text comprehension most strongly predicted by the number of diagonal lines and the size of the words that students produce. So were they using big words, they probably scored better on, or they did score better on the test. But then it was also related more to bridging than text-based comprehension scores, which was interesting, right? Because like I said earlier, bridging requires you to actually be making connections across the text. And so then when students had these recurrent properties of their language, then they also did better on the bridging questions as well. And so just to discuss what this means and wrap up a bit, what this shows is that the current study supports our hypothesis that the temporal patterns of students' language use can provide information about their comprehension and their performance on these language-based tasks. Natural language processing can provide important information, but they often miss out on this temporal stuff and this temporal information. And so dynamic modeling may be able to be combined with natural language processing to provide time-sensitive language assessments that really focus on how information is unfolding over time. And so our qualitative analysis of the recurrence plots suggested that comprehension processes could be observed through these visualizations without even looking at quantitative information, but that the RQA analyses were also able to account for variance in comprehension scores that move beyond the summative measures that we could calculate. And so in the future, we're going to look at this to move beyond these typical, these recurrence quantification analyses that I showed earlier. We're going to look at multiple dimensions, so we're not just going to focus on the word level dimension. Obviously, we're going to move into thinking about properties of the words and combining those together. There's something called multidimensional recurrence quantification analysis where you can look at these all together. And we're also going to do cross-recurrence, so looking at my discussions with you, and you can look at recurrent behaviors between two different people as opposed to against itself, which is really interesting as well. And so you can look at different types of speech. And then finally combine these with linguistic metrics to hopefully drive better feedback in our system in the future. So I'll thank my lab, and then I will take any questions.
We have time for maybe one, two questions.
Thanks. I have sort of a commenty question and a question. And the commenty question is, you use the word temporal to describe what you're looking at, but it almost sounded like what you're finding as important is, for example, reusing longer strings of words rather than reusing a word. So that sounds to me like a structural property of the text, but it's not when you reused that string of words, it's just that you reused it. If you had reused it at any point, it would have still appeared. So that's sort of, you can object to my categorizing it as structural or temporal. And the other question I have is, do you have a sense of what the distribution of these recurrence statistics are like in your population? Like if you're looking at something like recurrence rate or entropy, what is the distribution of that statistic in a typical kind of learner population that you're looking at?
Yeah, so they're pretty broadly distributed. I don't have it on these slides, but yeah, all of the statistics were pretty normally distributed, and I've done this on 3 separate groups of students now. I've done it on high school students and college students, and they're exhibiting very similar patterns, but they're all of the indices were normally distributed except the line number one, which I log transformed that one, but the rest of them are normally distributed. I think you are right about the thinking about temporal, and so a lot of it is different types of recurrence quantification can get at, like a continuous time series is going to look at that in a different sort of way. But one thing is thinking about, a lot of these do sort of start picking up on, if you have all of the, so you can do this with different metrics, and the visualization shows it, but then the quantification that I showed don't actually pick up on where they are in the plot. So if you have a lot of the line links right at the beginning or right in one area versus way later in the text, there are different indices. So I didn't show it today, but you can also do windowed recurrence. And so you can say, like, I'm going to take this time window across the text and slide it along and calculate these recurrence metrics across it. And that's when you can really start picking up on the temporality in a different sort of way and show when recurrence peaks and when it starts to go down in different areas. And you can change the window size as well and see where it's stable and where it's not stable. So.
Thank you. We're going to run out of time at this point.
Okay.
Thank you.